So if we look at these problems here, trying to find the missing pieces. Number one here is pretty straightforward because we have a right angle here. We know this angle then has to be 55 degrees because those three angles have to add up to 180. Now I've got the angles labeled A, B, and C. The sides then can also be labeled. Side little a is always across from angle big A. Side little b is always across from angle big B. And side C is always across from angle big C. Angle C is usually the right angle if there is one. So side C is the hypotenuse. The other two are legs, and it depends on which angle we're looking at, whether they're opposite or adjacent. So we were given the 35-degree angle, so let's work with that angle. So I would make A the opposite side and B the adjacent side. So if I'm trying to find B, let's do that first. I have A, which is the opposite side. I'm looking for the adjacent side. That's tangent. So I plug in what I know. The angle I have is 35 degrees. The opposite side I have is 8 inches. I am looking for side C, or side B, I should say, which is the adjacent side. So I will put this over 1 and I will cross multiply and divide. I get 8 divided by tangent of 35. 11.425 inches. Now I could, at this point, I could do a squared plus b squared equals c squared because there's a right angle here. But I just calculated this and there's a round off there in it. So I like to go back to original information. So I'm going to use this side and my angle. This is my hypotenuse. So I have the opposite hypotenuse. That is the sine. So I write down that definition and then I'll fill in what I have. I have the angle of 35. Opposite side is still 8. I am looking for C, the hypotenuse. Cross multiply and divide. 8 divided by sine of 35 is 13.948 inches. Now, if we'd had a little more time and you went to try to solve this one, what do you notice about it? This angle here has to be 60 degrees, good, because I have to add up to 180. So what does that tell us as far as our trig? Exactly, there's no right angle. That means we cannot use a right triangle trig, right? It doesn't mean we can't use trig, it just means we can't use right triangle trig. Now, because of the questions on the homework, I do want to do, before I jump into how do we solve that? How do we find those now if we don't have right angles? I do want to take a look at, we'll get it on the recording here, at least one of our homework problems. See, which one was it we did? We did 31? Okay, so let's do number 34. So for number 34, we have hanging in some sort of a harness. An 85-kilogram mass hanging down. We have angles here. This angle is 128 degrees, and this angle over here is 148 degrees. Well, what we really want from those angles is the angle from the horizontal. From the horizontal, this angle, yeah, this would be 90, so this has to be 38. Over here, this angle would be 58 degrees. Now we make an assumption. That assumption is dealing with the direction of the forces on these cables. We're going to assume that cable pulls that direction, this cable pulls that direction. Wouldn't make sense. They really can't push anyway. They have to pull. So this cable we're going to break down into two components, horizontal and vertical. I'll call that cable A. The horizontal component of cable A, which is this piece here, is going to be A times the sine of 38, or it's not sine, cosine of 38 degrees. Cosine of 38 is 0.788. So that is 0.788A. That is my horizontal. Now I'm going to jump down here to do the vertical component of A. That'll be A times the sine of 38 degrees. So sine of 38 is 0.616 A. That's the vertical component of A. Now then for B, I'm going to call this one B. I have a horizontal component and a vertical component. Bx, the horizontal component of B, is going to be B times the cosine of that angle of 58 degrees. So cosine of 58, 0.530. That's 0.530B. And then BY, the vertical, is B times the sine of 58 degrees. So sine of 58, 0.848 is the vertical component. Now let's look at the directions here. Both BY and AY are lifting up. The only thing that is pulling down is the 85. Now, this is not moving. So because it's not moving, we are assuming it is in what's called equilibrium. Yes, which means the sum of the forces has to equal 0. The vector sum of all those forces has to be 0. Well, we saw that in the vector sum, we could add it component by component. So since 85 is a vertical component going down, we only compare it to other vertical components, BY and AY going up. So the sum of those vertical components has to add up 85. So 0.616A plus 0.848B, those are the vertical components, has to equal that 85 kilograms going down. Now then in the horizontal direction, our sum of our forces has to be 0 as well. Well, B points to the left and A points to the right, so those forces are opposite directions. The magnitude of those forces has to be equal. So 0.788A has to equal 0.530B. So now it's a system of equations we have to solve. To solve a system of equations, this would probably be easiest to solve using substitution. So to do that, I'm going to solve for A. So I am going to divide by 0.788 to get A by itself. So A equals 0.530 over 0.788B. I'm going to divide this and see how ugly it looks. 0.673B. So that's going to go in here for A, right? So 0.616 times 0.673B plus 0.848B equals 85. Now you will notice I did not clear my calculator, and there's a good reason for that. I'm going to keep that number here, this divisor that we rounded to 0.673, I'm going to keep that out to a few places. So what I have here is this times that plus this times b equals 85. Does that make sense? So I'm going to combine 0.616 times that number. That's what's in my calculator times 0.616 plus the 0.848 is 1.262 we'll go with. B equals 185. Now to solve for B, divide by 0.1262 or 1.262. So B equals 85 divided by that previous answer. 67.34 kilograms of force on B. A then is 0.673 times B. So times 0.673, 45.32. Along the axis of A. Now you look at those, 67 and 45, that's like 113, 112. That's much bigger than the 85 pounds. But you got to remember, they're not pointing directly up. They're pointing off at angles. So yeah, the bigger they are. And that's something you've got to look at. Because this is basically a triangle, A plus B has to be larger than this. If it's not, you know you made a mistake somewhere. A plus B is smaller than that, it can't work. There's actually a notation that comes from this called Bose notation. What Bose notation does, it says we're going to start at the known force. It's the 85 kilograms going straight down. Looks like that. That's 85 kilograms long, goes straight down. We know both its magnitude and direction. It's a known vector. This was 128 degrees total. So this was 38 degrees here. So our next vector, we're going to go around this thing counterclockwise, is going to be vector A that goes off here in this direction. That's magnitude A. That's 38 degrees, which would make this angle in here 52 degrees. And then next we'd have vector B here that goes this direction. Has to bring us back to this tail. These vectors, to add up to 0, they have to make a complete circuit, get back to 0. So if this starting point here was at 0, the vectors have to add up and get back to 0 net force. The direction on B, well, this was 148 degrees here, which meant this direction from vertical was 32 degrees. So that makes this angle 32 degrees. So then you can find this angle over here of what, 96 degrees over there? So this does not form a right triangle, does it? We have all three angles and we have one side, which is going to fall into what we're going to be working on today. Like that second example we started off the class with. Let me get those numbers down again. 50, 70, 60, and 25. So let's go back to that triangle. So this is what I had given you. From that, of course, we can label this side little a, little b, and little c. And we very quickly found this angle here had to be 60 degrees because those three angles have to add up to 180. There are no right angles here, so we can't use right triangle trig. This is what is called an oblique triangle. An oblique triangle is just a fancy word for any triangle that's not a right angle or not a right triangle. One of the possible formulas for solving an oblique triangle, which is going to apply on here, is the law of sines. The law of sines is a ratio, compares the ratio between the opposite side of a triangle and that angle that's opposite it. So angle C is opposite side C. So it's the ratio between those. We discussed briefly that the largest side is always opposite the largest angle. And of course, the opposite of that, the smallest side is opposite the smallest angle. Well, the law of sines takes advantage of that fact. So it's not the ratio of the side to the angle itself, it's the ratio of the side to the sine of the angle. Now, depending on the textbook you look at, the law of sines can be written in one of two ways. The way I'm going to write it, it's going to look like this. The length of side A divided by the sine of angle A, its opposite angle, is a constant ratio for that triangle. So the length of side B divided by the sine of its opposite angle, which would be angle B, is the same as the length of side A divided by the sine of its opposite angle, angle A, which will also be the same as the length of side C divided by the sine of its opposite angle, angle C. Now, some textbooks write it the other way, sine of A over little a, sine of B, and little b on bottom, and so on. It doesn't matter. It's the same ratio either way. I just like it this way because it's, for some reason, more comfortable to me to write it that way. So what does that mean? Well, it means we have to find a side and its opposite angle. Here we have only one side. That side is 25. What's its opposite angle? The 70. There we go. So we have that pair. So that means we can use the law of sines. So that side is 25. It's going to be over the sine of 70 degrees. Now we can find any other side here. Which side do I want to find? Let's find C. What is its opposite angle? 50. So 50 degrees. So to find side C, we're going to cross multiply. 25 times the sine of 50 divided by the sine of 70. Now you have to be careful to make sure you close your parentheses in your sign. We get 20.38. So C over here is 20.38 feet. Now let's just take a second to look at that and see if it makes sense. Does it make sense that this side would be shorter than this side? Well, is this angle smaller than that angle? Yes. Now before we find side B, before we do any calculations there, what do I know about the length of side B compared to those other two? It better be between them. Yes, because that angle 60 is in between them. So we're going to go back to that 25 over the sine of 70. Now it'll be B over sine of 60 degrees. And we'll cross multiply and divide. So 25 times sine 60, make sure you close the parentheses, divided by sine of 70. 23.04. And sure enough, it does come in between those two lengths. Now the case we just saw here, is one of the possible cases where we have two angles and one side. In fact, the side was opposite one of the angles. Another case we could have is two angles and one side where that side is what's called included. Included is just a fancy word for between. So let's do A, B, C. Let's call this angle here 40 degrees. We're going to call angle here, A here, 65 degrees. The included side would be this side right here. Let's call that 40 inches. So my sides, of course, this is little a, little b, and little c. Do I have a side and its opposite angle right now? Well, 40 is my side. The opposite angle would be B. I don't have that angle, but we can get it, right? What's that angle have to be? 75 degrees. So then I can just jump right in. I've got 40 over the sine of 75 degrees. Technically, I probably could write inches in there so I keep my units constant, but I don't have to. Now, doesn't matter which side I find next. I'm going to find side C because it's the smallest one over the sine of 40 degrees. I will cross multiply and divide here. So 40 times sine of 40 divided by sine of 75 gives me 26.62 inches for C. Again, that makes sense because 40 degrees is smaller than 75. To find side A, we're going to go back to that 40 over the sine of 75. That is our side and opposite angle that we know. And we're going to find A over sine of 65. Now 65 is between 75 and 40, so we know that hopefully this will give us a length in between those other two lengths. 37.53. Come on. And that is comfortably in between those other two lengths. So anytime we have two angles and one side, this law of sines applies and works beautifully. Because if we have two angles, we essentially have three angles. Where we have to be careful is where we have two sides and one angle. Now, if we have a case here where we have two sides and one angle, and the angle is what we call the included, what would that look like? Well, I might tell you that side A here is 40 feet, side B here is 35 feet, and angle C here is 48 degrees. Do I have a side and an opposite angle? No. Can I get one? Not right now, not with what we know. So for this case, we cannot use law of sines. Well, not tomorrow because you guys are gone for conference, but on Monday, we use law of cosines. That's what applies to this. That's a two sides and an included angle is law of cosines. However, the complications with having two sides and one angle doesn't end there. So we're going to have another case here. And in this case, we have two sides and one angle. And our angle is opposite the longer side. The reason I stress longer is that's very important. Since the longer side is the opposite side, we're good to go. Now, rather than drawing out the triangle, I'm going to list out my pieces here. I've got angles A, B, and C, sides little a, little b, and little c. If I tell you that angle A is 52 degrees, side A is 48 feet, and side C is 39 feet. Is the angle opposite the longer of the two sides? Yes. So the angle or the angle is opposite the longer of the two sides we're given. Now there's a third side that we don't know, but that doesn't matter yet. So angle A here is 52 degrees. Side A is 48 feet. Side C is 39 feet. So now we can find angle C over here. We know angle C has to be smaller than angle A. That's very important. So we're going to use 48 over the sine of 52 degrees equals 39 over the sine of angle C. Now note here that when we cross multiply and divide, we are not finding angle C, we are finding the sine of angle C, because it's sine of C. So we've got the sine of 52, close parentheses, times 39 divided by 48, gives us 0.6403. So C itself is the inverse sine of that 0.6403. This again is one I keep in the calculator. Second sine, second answer. 39.81 degrees. So C is 39.81 degrees. $88.19. Does that look right? That looks right to me. So now we can find side B, just like we did up above. We still have our 48 over the sine of 52 degrees. We're looking for side B over the sine. Now we do have to use that angle. There's just no way around it. We have to use an angle we calculated. So 48 times sine, that angle, oops, that's not it. 48 times the sine of 88.19 divided by the sine of 52 degrees. Get 60.88. Yes, it makes sense. That has to be the longest side. Our next case is where we start to have problems. We have two sides and one angle, but the angle is opposite the shorter side. Let's take a peek. So let's say I tell you that A is 28 degrees. Side A, let's go with 32 feet. But side C, oh, let's make this interesting. We'll go 55 feet. So what that means for us is when we draw out this triangle, I'm going to draw it here with my angle A first. Angle A here is given to be 28 degrees. This is going to be side little c up here, which is given to be 55 feet. Now it makes perfect sense to draw it like this, right? This would be little b here, this is little a. However, that's not the only way it could possibly be drawn. Because this opposite side is shorter than this side here, that 32 could go this way. Angle C could be obtuse. Since angle C is bigger than angle A, we know, or side C is bigger than side A, I should say, we know that angle C has to be bigger than A. We don't know how much bigger. It could be, well, it can't be hypotenuse because there's no right angle. Yeah. When we set this up, we're going to have 32 over the sine of 28 degrees equals 55 over the sine of C. And we're going to cross multiply and divide. Sine of 28 times 55 divided by 32. 0.8069. Which means C is the inverse sine of 0.8069. So do second sine. We get 53.79 degrees. However, this is where we got to refer back to that unit circle once again. Remember when we did that unit circle, that sine of 0.8069, this is 1 here, so 0.8069 is probably somewhere in here. There's that sine right there. This has given us that angle of 53.79 degrees. However, there is another spot on the unit circle that has a sine of 0.8069. And it's right here. Let's get back there. That has a reference angle of 53.79. Both of those have the same sine. Of course, this angle here is going to be the supplement of that. 180 minus that is 126.21 degrees. We have no idea which one of those angles is really angle C here. So we have to have a picture or some information. If we know that angle C is acute, then we know it is the 53.79 degrees. If we're told that it's obtuse, then we know it's the 126.21 degrees. And then, of course, that drastically affects the length of side B here. Because then B could either be rather large or really kind of small, depending on which one C is. So when we have that case where the side, we have two sides in one angle, and the angle is opposite the shorter of those two sides. We need to have more information. We'll talk about that more in class on Monday. For right now, I believe I've got to give you a new packet. And in this new packet, is it in this packet? Oh, yes, it is. 387 and 388 is still in this packet? No, it's not. I'm going to get you a new packet. It is. It's kind of cool. So on page 387, 388, it'll be 1 through 27, the odds. Do you have that one? The packet I gave you may have been a bigger packet. Okay, so it is in your packet. Good. So I don't have to give you a new one.